In a previous video, I said that a resistor is a component that limits current. It limits the flow of charge. Let's presume that I have a resistor and I don't know what the value is. Normally, I would just take an ohm meter and I would put the leads of the ohm meter across the resistor and I'd read the resistor value. But let's assume I don't have an ohm meter, but I have a battery and I have an ammeter and I have a voltmeter. So let's see how I can measure the value of this resistor. So I'm going to take my battery. I'm going to take the positive terminal. I'm going to connect it to an ammeter. I'll call A. And connect that to one end of the resistor. And I'll take the other end of the resistor and I'll connect it to the negative terminal of my battery. Minus, plus. Let's presume that the battery is a 1-volt battery. And I'm going to take my voltmeter, I'm going to put it directly across the terminals of the resistor. We'll call this V for voltmeter. And I'm going to take a series of readings. Now I put the voltmeter right across the resistor terminals because this wire is going to have a little bit of parasitic resistance. And I don't want to measure that. And the battery will have some series resistance associated with the battery. So by putting the voltmeter right across my unknown resistor, I don't measure these parasitics that are in the circuit. Let's presume that I read 1 volt on my voltmeter. So the parasitics are very small. And I measure 1 amp. 1 amp of current flow in this resistor. So I can calculate the resistor by a very simple equation. Resistance is equal to the voltage across the resistor divided by the current I going through the resistor. This is called Ohm's law, and we'll talk more about Ohm's law in the future. So in this case, I can calculate my resistance. R is equal to 1 volt across the resistor divided by 1 amp through the resistor is equal to 1 ohm. We use the Greek symbol omega to denote ohms. So that's rather simple. Let's think about what's going on in this resistor. Now, a resistor is a component that dissipates energy. It produces heat. If we have enough current flowing in this resistor, enough electrons moving through the resistor, these electrons bump into other atoms in the resistor and it creates heat. This bumping around produces heat. Think of a meteor. As this meteor falls into the Earth's atmosphere, the air acts like a big resistor. The meteor continually hits these air particles and it creates heat, and the meteor eventually burns up in the atmosphere. Now a similar thing happens in a resistor, not to such a degree, but to a lesser degree. As the electrons collide with the particles, they produce heat, just like that meteor entering the Earth's atmosphere. And there's a very simple equation that we can calculate the energy or the power dissipated by this resistor. And the equation for this is P for power is equal to the current flowing through the resistor times the voltage across the resistor. In our simple example, the power would be 1 amp times 1 volt across the resistor would be equal to 1 watt. 1 watt of power dissipation in the resistor. So if we wanted to go to our local electronics store and we wanted to buy a resistor that would work in this circuit, we would know that that resistor could dissipate 1 watt of power. So we would want to buy at least a 1 watt resistor. If we bought a 1/4 watt resistor by mistake, it could easily burn up. That would be very dangerous. So to be safe, maybe we would buy a 2 watt resistor. Let's erase this. Let's repeat Ohm's law for resistance. Resistance is equal to voltage divided by current. So if we have a circuit and the current is very small in the resistor and the voltage is very large across the resistor, then a small value in the denominator of current will produce a very large resistor. Large voltage will produce a large resistor. In fact, if we had 0 current, we would have infinite resistance. We would have an insulator. But this equation doesn't tell us how to make a resistor. There's also another equation for resistance that's equal to rho times the length of the resistor divided by the cross-sectional area of the resistor. Now rho is the Greek letter that we use for resistivity. Resistivity is a function of the material used to make the resistor. Different materials will have different resistivities, and we can look these up and know what the resistivity is for our particular material, whether it's a carbon resistor or aluminum resistor or whatever kind. Now the length and the area, let's discuss that. Let's say that we have a resistor with a cross-sectional area A and a length L. The length of the resistor is L and the cross-sectional area is A. Now we have a terminal on this end of the resistor and one on the other end. So the current is flowing in this direction in the resistor, current I. So by knowing the resistivity of this material of the resistor, the cross-sectional area and the length of the resistor, we can calculate the value. Let's talk about resistivity. The resistivity, rho, for aluminum metal is equal to about 2.8 times 10 to the minus 8 ohm meter. The resistivity of another material, Teflon, is much higher. It's equal to about 1 times 10 raised to the 24th power ohm meter. Now what this tells us is that if we had a 1 meter cube of aluminum, which is huge, that would have a very small resistance, about 2.8 times 10 to the minus 8 power, very small. But if we had the equivalent cube of Teflon, 1 meter square of Teflon, it would have an enormous resistance. And that's because in the aluminum, it's a metal, and the electrons are very free to move. They're very mobile. However, in the Teflon, the electrons are bound very tightly to the atom, and it takes a lot of energy to separate the electrons and to make them move. So this Teflon makes a very good insulator, and the aluminum makes a very good conductor. Let's do a resistor calculation using resistivity. Here we have a sheet of aluminum metal that's on an integrated circuit. It's very thin. It's 1 micron height. It's 10 micron wide, and it's 100 micron in length. The current is flowing in this direction in this piece of aluminum. Let's calculate the resistance of this strip of aluminum using the resistivity equation for resistance. Resistance R is equal to the resistivity of the aluminum times the length, in this case, which is 100 microns, divided by the cross-sectional area, which is, in this case, is this area here, which is 1 micron times 10 microns. So this we can rewrite as 2.8 times 10 to the minus 8th power. This is ohms meter, and we want to convert meters into microns, so we know that 1 meter is 10 to the 6th microns, because there's 1,000,000 microns in a meter, times 100 micron length, and divided by the cross-sectional area, 1 micron times 10 microns. Now this micron cancels this micron cancels this micron, and this meter cancels this meter, and we're left with 0.28 ohms, which is a rather small resistor, but still not negligible.